have gotten a consent from everyone. Okay, so switching my camera. Here we go. It's not as easy as at my school computer. Switching the camera is a lot easier. Look, I had to leave a post-it note for myself because I keep forgetting to do that. Okay, so if you've not been with us before for live class or class from my guest room, the best thing you can do is to hover your mouse over my screen, my note screen, and you should see a little push pin, and you can just pin my screen to your computer screen. That way you don't see that tiny little paper there. You'll be able to see the whole thing. If at any point you have questions, please just shout them out. We know our class is small enough that we can just shout out questions. Interrupt me if I'm going too fast. You just let me know, okay? All right, here we go. Gosh, if this doesn't look fun or what? So we've spent the last 4 months, like I said, talking about derivatives, applications of derivatives, rules for derivatives. And today we are going to be talking about antiderivatives. So here we go. Let's talk about what that means. So we've been, in the last 4 months, using a function to find its rate of change, right? We would take the derivative. For instance, if I gave you the position function, we would take the derivative to find the velocity, or the derivative again to find acceleration. What we're going to start today is, what if we know the derivative and we would like to find the original? We're going to call the original the antiderivative. But basically, we're just going to be going backwards. I'm going to give you the derivative. You're going to give me the original. The process, just some vocabulary here, is called antidifferentiation. Okay? Going backwards, right? Reversing a process, which we've been doing that for years in Algebra 2 and in pre-calc. We've talked about reversing functions or undoing functions. So we'll come back to that. Before we do that, let's talk about a little bit of notation. If our, let's write this way, derivative, antiderivative. I'm not going to write a whole lot here. Some of them are a little more obvious because we already know, right? For instance, if our derivative is called f prime of x, well, then the original is called f of x, right? That we know that. In fact, we could do the same thing with y prime or dy dx. I'm not going to write down the ones that we still already know. However, if our derivative is already called f of x, and we're going to go backwards and find the original, we'll call the antiderivative capital F of x. Just because that's the only notation that we have, okay? So if our derivative is a lowercase letter, we'll use a capital letter or an uppercase letter to note that it is an antiderivative, okay? Otherwise, all the old notation will still stand for us. All right, here we go. Let's do a couple of let's call them easy ones. It says find an antiderivative for each. All right, so they're telling us the derivative, f prime of x, is cosine of x. I would like to know then what was the original function. And so one question you could ask is, what is cosine the derivative of, right? And I'm not gonna call on anyone right now, but I would love it if a couple of you would unmute yourself and just tell me, what is cosine the derivative of?
Negative sine of x?
Close.
Oh.
Okay, so Sydney, the derivative of cosine is negative sine. I want you to think about backwards. What is cosine x the derivative of? And anyone can help her out.
Isn't it just sine?
It's just sine x. I know, and I did not bring everything home with me. I wish I would have. Some of you, if you have it handy, remember that derivative rules sheet I gave us at some point? Maybe it's on the back of a note sheet for Unit 3. Like if you have your Unit 3 notes packet, I think it was on the back of the cover sheet for that. It's all of our derivative rules in one place. And so if you have that, that might help. And I don't have mine with me. I realized that this morning. I should have brought that home. Because it's hard to go backwards at first, Sydney, especially with a sine and cosine. We're going to, go crazy. But I think we could all agree the derivative of sine is cosine. And the great news about these is we're so comfortable with derivatives that it's going to be much easier for us to check our answers, right? Because if you want to check this, like I just did, you're going to take the derivative and see if you get back to cosine x. Okay. I'd like to see if we can come up with another answer for this one. Is there another function whose derivative will be cosine x? Anyone? Anyone taking AP Physics C right now? No? Okay. How about this? If I'm saying this is f of x, and I go to find its derivative, well, the derivative of sine x is cosine x, and the derivative of 2 is 0, isn't it? So isn't this also a possible answer? What about this? Does that also work? And here's what I'm doing. I'm coming up with some possible functions whose derivative is just cosine x. So I'm not changing this piece, right? The derivative of sine is cosine. The derivative of sine is cosine. The derivative of sine is cosine. But if there's a constant out here, don't we know the derivative of a constant is 0? So no matter what number this is, when I go to take its derivative, it's going to go away. So we could generalize this. In fact, I'm going to write general antiderivative is going to be f of x equals the sine of x plus any constant. And I used a capital C for a generic constant. Because here's what happens. When we go backwards, we lose information that could have been there. I won't say we lose it, but we don't know. When we take a derivative of a constant, it goes away. So then when we try to go backwards, we don't know what would have been there. Does that make sense? So when we take an antiderivative, we're always going to put a plus C at the end to say there could have been a constant. We don't know if there was one, if it was 0, if it was positive, if it was negative. We have no idea. Okay. All right. Let's slide to the next one. This is different because it's not a trig function, so it's not necessarily something you're going to find on your derivative rules to memorize sheet. What about this one? If f of x equals x squared, I want to think what function would have a derivative of x squared? And I want you to think about it for a minute. I'm going to give you about 60 seconds here. Do we have any thoughts? Anyone want to take a stab at it?
Would x to the third over 3 work?
Well, let's check. So first of all, before I write that down, if my derivative is already called f of x, its antiderivative will be called capital F of x. And Grace said, does x to the third over 3 work? I'm just going to write that as 1/3 x cubed. Same thing, right? Let's check. Because again, I said it before, we're going to be a little uncomfortable finding these antiderivatives. But once you just take a stab at it, you're so good at taking derivatives, do a quick check, right? So let's check. The power rule says bring the 3 down in front and multiply. 3 times 1/3 is 1. And then subtract 1 from the exponent. I think it works. I love it. The only thing I'm going to make sure I do is put a big old plus C at the end. So Grace said x to the third over 3. Grace, you mind if I ask how you came up with that? What was your thought process?
I knew that because of when you take the derivative, you subtract 1 from the exponent, so I added 1.
Okay.
And then I had to think about how to divide that to get 1, so I did the 1/3.
Perfect. So you just kind of said, look, I know it has to be a higher power by 1, and then I need to figure out how to get just a 1 in front. I love it. Here's what I'm going to write down. This is what we, have been doing since August. The power rule for derivatives we're so comfortable with. If you're going to take a derivative, like if I were going to take the derivative of x squared, the rule says you bring the exponent down in front and multiply. And then we said, let's subtract 1 from the exponent, right? We multiply the exponent and then subtract 1 from the exponent. Well, earlier I said an antiderivative is reversing that process. This is an inverse operation, which means if we're going to do this to go backwards, not only are we going to do the opposite operations, we're going to do them in the reverse order, thinking inverse. So instead of multiplying and then subtract 1, let's add 1 and then divide. And I went ahead and wrote by the new exponent. This is the power rule, as Grace just said, in words. We're going to write it down more formally, but this is the power rule for antiderivatives in words. We're going to add 1 to the exponent, and then we're going to divide by the new exponent. So if we go back up here, we had x squared. We're going to add 1 to get x cubed, and then we're going to divide by that new exponent of 3. Okay? So let's write this down a little more formally. We had a very similar box when we were talking about the power rule for derivatives. If little f of x equals x to the n, right? The variables on the ground, the numbers in the exponent. Then we'll say capital F of x equals x to the n plus 1. We add 1 to the power, and then we divide by that new power of n plus 1. And just like when we were talking about derivatives, this is for any real number n. So n does not have to be a whole number. It does not have to be an integer. It can be a pi. It can be a radical 7. It can be a negative 1/3, right? So as long as it's a real number, the power rule will work. Okay? So that's a little more formal. I think we're just going to say you're going to add and divide, add and divide, add and divide. All right? So let's take a look at some examples here. We'll do the first one a little slower. So it says for each function, we're going to find the general antiderivative. And that general just means we're going to have a plus c at the end, because that's all we can do right now. And again, we can check every single one of these if we want by just taking the derivative and seeing if we get right back to where we started. All right, here we go. We have a function that has 3 terms. We're going to use some of those rules for derivatives, like the constant multiple rule and the sum and difference rule, right? If I have 3 terms, and if I'm allowed to take the derivative of each one separately, I should be allowed to take the antiderivative of each one separately. And by the way, we might be guessing on some of these things, and we're just going to take a stab at it, and we'll see if our guess works in the end. All right, so here we go. The 2 is going to stay there because it's a constant multiple rule. Now we're just dealing with that x squared, which Grace already said on that last slide. The antiderivative of x squared is x to the 3rd divided by 3. We'll clean it up later if we want to. Next term, I have a minus, and then I have a 5 times, right? There's another constant multiple. So I went ahead and wrote minus 5. Right now, this is an x to the 1st. I'm going to add 1 to the exponent to get x squared. Divide by that new exponent. So divide by 2. Now, the third one's a little different because there are no x's there. Now, you could write x to the 0 if you really want to, but let's think about it this way instead. What is 6 the derivative of?
6x.
6x. Perfect. And so we've taken the antiderivative of all three terms, and then we'll get just that giant plus c at the end. We don't know. There could have been a minus 17. There could have been a plus 1/3. We don't know. So then if you want at the end, if you want, especially if there's some reducing to do, you can clean this up, but there's not much to clean up. I'll probably write it as 2/3 x cubed minus 5/2 x squared plus 6x plus c. Didn't really get me anywhere because nothing reduced, but I feel it looks a little nicer, but we didn't actually do anything there. So certainly you didn't have to. All right. Let's go to the next one. We have f prime of x equals negative cosine of x. This is very similar to the one we did up here, right? This was just cosine x. Well, hey, now that we've talked about that constant multiple rule, maybe we think of this as -1 times cosine x. So if this is called f prime, the antiderivative will be just called regular old f. The constant multiple rule says the -1 will stay there. And we've already said the antiderivative of cosine x is sine x. We just need to make sure we tack on a plus c. All right, let's talk about this third one here. If I were going to, I'm not going to, but if I was asked to find the derivative of this, what would I do first? Seth, can you help us out here? If we were going to take the derivative of this, what might we do first?
I would move the square root to the top and make it like a negative exponent.
Perfect. We would write it as a power, right? The reason I say that is because if you would use the power rule to take the derivative, you probably should think about the power rule for the antiderivative. So again, we're just going to take a stab at it. We don't know. So you're right. Let's take that x minus 5 and bring it to the top and use a -1/2 power. All right. Now let's see what happens here. So this was still the derivative. So we'll say y equals the -2 stays there. And now let's deal with this. I know we might see something like, oh, it's like a chain rule. But the good news is the derivative of the inside is just 1. So it wouldn't have actually been a chain rule. So we'll come back to that, especially tomorrow. So we're going to add 1 to the exponent. And when I add 1 to a -1/2, I get a +1/2. And then we need to divide by that new power. Dividing by 1/2 doesn't look so hot. Maybe we should think of multiplying by 2. Same thing, right? So how about -4 times the square root of x minus 5? Whoops, and I almost forgot. Plus c. So what I did at the end, you don't have to do. You know that. You never have to simplify your answers. But we learned very quickly last semester that, yeah, you can leave all of your answers unsimplified. But A, it starts to become very difficult to check your answers with mine. And B, it becomes very difficult to work with them, right? We know we're not just going to be finding antiderivatives this year. We're going to be using them to do different things. So it will be in our best interest to practice cleaning them up as best we can. Okay. Again, best thing we could do, we could take the derivative of all three of these and see if we get back to where we started. Okay. Because you will feel in the next few days, you will feel like you're making guesses. You will feel like, I don't know if I can do this. Well, go ahead and do it. But if you're not comfortable, check it. Okay. All right. Perfect. Let us flip our page over. Okay. So let's take a look at these two. This first one, we've got g prime of theta equals -2 cosecant squared theta minus 3 theta. So I'm fine with this, right? We've got two pieces. This piece doesn't bother us. This is a power rule. I want you to take a look at this for about a minute here and think about what you would do. And maybe some questions you could ask is, what would I do if I was going to take the derivative? Or is there some way I can make it look different? I just want you to look at it. I'll stop talking. I have no idea how much time passed. Could have been 60 seconds, could have been 30. I'm horrible at time. But let's just throw out some thoughts. Again, it might not be right, and don't let that bother you. Let's see. Megan, did you have anything you wanted to try on this one, or anything you were thinking about? Megan said she couldn't think of anything. That's okay. Kat, what about you? What'd you try on this one? I'm just going to go ahead and open it up. Did anyone have anything they wanted to try? These are not easy. Here with Megan. You okay? Couldn't think of anything.
I factored out a negative.
You did what?
I factored out a negative.
Factored out a negative. That's fine. You said they both have a negative, so let's get rid of it. That's absolutely fine.
Could you like apply the square that's over the cosecant to the whole thing, and then like the whole first term, and then add like a plus to the exponent, and then divide by that 3 maybe?
So is that kind of what you mean?
Yeah.
I shouldn't have used a pencil. I know that doesn't come across very well. If we were going to take the derivative, Sydney, you are absolutely right. If we are going to take the derivative, the first thing we do is we would rewrite that cosecant theta. Well, we'd write it as cosecant theta squared. I love it. But then what rule would we have to use? The chain rule, right? Makes it more exciting when you kind of sing it a little bit. We'd have to use the chain rule because it's not just a theta squared, it's something else squared. It's the cosecant of theta. And have we talked about reversing the chain rule today? No, we have not. Now, we're going to talk a little bit about reversing the chain rule tomorrow, and then not again until Unit 6. So we'll talk about a special case, but we don't actually have a reverse for the chain rule at this point. So I love where your head was, Sydney, because it's kind of where I was trying to lead people. It's like, well, how would I take the derivative? You're right. We would do something like this and then go ahead and apply the power rule and the chain rule. Unfortunately, we don't have a reverse for the chain rule. And even once we do, it's not going to work here. I know that doesn't make a lot of sense yet. You hate it when teachers just tell you, you don't have the rules yet. Did anyone pull out their derivative rules? Was anyone? Yes. I'm going to rewrite this, and this is why I know this was difficult. And that's why Megan and Kat and some people just kind of stared at me blankly, like, I don't actually know. What if I were to write it this way? I know, Ansley, you said you pulled out the negative, but I actually left it in there. In fact, I'm going to use my hand and cover that up. That second term, that negative 3 theta, I don't want to see it right now. You see what I did here? I know this is kind of odd, but I just took the 2 and I pulled it out in front, but I left the negative there. Does anyone know why I did that?
Isn't the derivative of cotangent negative cosecant squared?
That's exactly right. We know this one. We have this one memorized. That's what's going to bother some of us, is that we're not going to, first of all, we took 2 weeks off. And if you did anything like I did, you just turned your brain off of work. I turned off my work email. I turned off my... So I get it. We're warming up today, right? Which is why it's a good day to do this. This is something we know. I'm going to take my hand away and underline this. This, we have this memorized. That's why I left the negative with it. If you look at your derivative, I'm going to write it up top here. The derivative, if you look at your derivative rules sheet, the derivative of cotangent x is negative cosecant squared x. Folks, that's why this one was so hard for us, because we weren't thinking that way. We had just finished talking about the power rule. Our brains weren't there. So if this is the derivative, I'm ready to take the antiderivative. The constant multiple, the 2 is going to stay there. The negative cosecant squared theta becomes cotangent theta. And then we'll use the power rule on this second piece, right? There's no trig there. So we'll add 1 to that exponent. So I have 3 theta squared, and then divide by 2. That's what makes that one, I think, a little tricky. Okay. So here's the deal. As we're starting to just kind of get used to antiderivatives, we have very, very, very few rules. I haven't talked about a product rule. I haven't talked about a quotient rule. I haven't talked about a chain rule. All we really have is the constant multiple rule, the power rule, and the rules we have memorized. And maybe we just jot that down. Current or available rules for us. Obviously, when we get to Unit 6 and we talk about methods for antiderivatives, we'll have a lot more. But current or available rules, if I can spell right, would be the power rule, the constant multiple rule, which just gets constants out of the way, and then any rules that we have memorized. That's it. And I know that feels not great. You're going, oh, we don't have a lot, but I think that actually makes it easier. The fewer rules you have, the easier it is to kind of say, oh, well, I can't use that. I can't use that. So it must be that. Okay. So with that being said, let's talk about the next one here. I have y prime equals 4 over the square root of 1 minus x squared. Now I'm going to flip my paper real quick because we already did one like this today. On slide number 4 down here, remember we had a number divided by a square root. And we said, oh yeah, let's just use a negative exponent. The chain rule is not an issue because it's just a derivative of a 1 in there. So, we've done something like this. What makes this one different is there's a squared in there. So if, I've said that now 3 times. If I were to treat it like I did the one on the front and rewrite it using that negative power, I see a huge problem. And I know it's hard to see because you don't know a lot of rules yet. The problem I see is that if I just try to use the power rule, I've got this thing on the inside that's not just a linear function. It's a 1 minus x squared. And so we'd use the chain rule there. And Mrs. Patton just says we don't have a reverse for the chain rule. That's a huge red flag for us. So I'm going to just write down chain rule question mark. We don't have a rule for that. So here's what I'm going to do instead. That constant multiple rule, I'm going to slide that 4 out in front because I think it was a bit of a distraction. I know I haven't given you a lot of time to look at this one necessarily, but I just slid the 4 out in front. And I want you to just look at the piece that I circled in red. Does that look familiar to anyone? And you might need to look at your derivative rule sheet, and that's okay. It should look familiar. And again, I know we took 2.5 weeks off. What is this the derivative of?
Inverse of cosine?
Close. I think just sine, because the inverse of cosine has a negative on top, doesn't it?
Yeah.
Yeah, that's
Yeah.
all right, but I'm glad you saw it. This right here is the derivative of inverse sine x. Gosh, that's been a while, hasn't it? That 4 out in front, we're just going to leave it there. And then we get a big old plus c. My point here is please do not overcomplicate these. Sometimes it's staring us right in the face. We know these, and it would be in your best interest in the next day, few hours before you do your homework, to really look through your derivative rule sheet just to get some of those juices going again, to remind yourself of the things that we should still have memorized, the things that we want to look for. Okay, we would have created a huge disaster had we tried to reverse the chain rule, because we don't have a reverse for the chain rule yet. Okay? All right. So I love these two because it really reminds us that if it looks complicated, it's probably something we have memorized. Okay? All right. Let's do a couple more. So all we've been doing is finding what we call that general antiderivative. The general antiderivative is a whole plus c, plus c, plus c. And that's all we can do unless we are also given one point that the original graph passes through. We call this point an initial condition. Basically, they're saying it's where you're going to start. And we had this before when we were doing, back in Unit 2, when we were graphing original functions, and in Unit 4, it said, sketch a graph of the original, given that the original starts at the point 0, 1, or something like that. Okay, basically, this initial condition is going to allow us to find the value of C. Right? So the general or generic antiderivative is going to have a big old plus C at the end. But if they give us more information, we'll be able to figure out what C is. And we call that a particular solution, the answer. All right, so here we go. We're going to find f of x if f prime of x equals tangent x over cosine x, and the graph of the original passes through the point pi comma 1. So they're giving us the derivative and a point on the original, a point on f. All right. So I'm actually going to slide right back here. Remember how we talked about available rules for us? Power rule, constant multiple rule, or it's something we have memorized. This is a quotient. We don't have quotient rule in our list. I think that's actually helpful. I'm telling you. And if it's not like an x squared or x to the 1/2, then we're certainly not using the power rule, which means this is something we should have memorized. I feel like as soon as we see trig functions, it's our only option right now. So those of you that have your derivative rule sheet out, do you see this anywhere? You might need to use your imagination a little bit, or imagination, maybe not the right word, but be a little more creative.
Is it the derivative of the secant?
It sure is. I'm going to write this up at the top. From our derivative rule sheet that I apologize I didn't print out, the derivative of secant x is secant x times tangent x. Well, remember, secant x really means 1 over cosine x. Oh, well, that's exactly what we have. We have tangent x times 1 over cosine x. So maybe I'll come down here and write that out. F prime of x is really, I'm just going to spread it out like an accordion, right? 1 over cosine times tangent, which is secant x times tangent x. So you just have to be willing to think a little more creatively in that sense. When you see trig functions, you're going to ask yourself, can I make that look a little bit different? So if the derivative is secant x tangent x, that means the original is just secant x plus c. Don't ever forget the plus C. I know it's going to be something that we forget all the time, especially today, because it's so new. So this is the general antiderivative. But they also told us that on the original function, we're going to pass through this point. They're telling me when x is pi, y is 1. Let's go plug that in. Y is 1 when x is pi. I'm going to be able to find c. Let's see, the secant of pi. Well, the cosine of pi is -1. 1 over -1 is still -1, which means c equals 2. Now, that's not my answer. They didn't say find c. They said find f of x, which step right back up there. And we can now say f of x equals secant x plus 2. So we've only added on one thing, right? I understand we're still a little uncomfortable with the actual act of an antiderivative and you know, kind of making things look different. We only added one step, and that's to plug in the point they gave us to find our value for c. Okay. All right. So I know we've got about 3 minutes left, so I'm going to skip the next slide, and I'm going to go straight to the last one. Okay. I feel like if we do the last one, it kind of covers that one before it. All right. It says find a function f of x if we know these 3 pieces of information. They're giving us the second derivative equation. Then they said f prime of 0 equals 4. They're giving us a point 0.4 on the first derivative, aren't they? F prime of 0 equals 4. The first derivative is 4 at 0. And then they said f of 1 equals 1. Well, they're giving us the point 1 on the original function. So they gave us the second derivative. They're asking us to find the original. Well, just like when they gave us the original and said find the second derivative, we took the derivative twice. We're going to take the antiderivative twice. So if I'm starting with f double prime, then the first thing I can do is find f prime. And I'm going to kind of go through it a little quicker. I have the 12. I'm going to add 1 to get x cubed, divide by 3. Some of you will do all of this in your head and simplify as you go, and that's fine. Plus, I have the 6. I'm going to add 1 to the exponent to get x squared, divide by 2. The antiderivative of 4 is 4x, so I have a minus 4x, and then plus c. And I think we would all appreciate if we would reduce our fractions. Okay. Before I take the antiderivative again, let's find our c, right? We have a piece of information about the first derivative, so we should use it here. On the first derivative, the y value is 4 when the x value is 0. Oh, that's actually pretty nice, which means c equals 4. I know I'm running out of time. If you have to leave, you leave whenever you need to go. I'm almost done, I promise. Without the bells here, I know you feel like I'm capturing you. I'm so sorry. So, oh, I wrote plus c. I meant to write plus 4. Gosh, that's what happens when I talk and write at the same time. All right, last thing. Now we have a complete first derivative. Now we can take the antiderivative one more time. So the 4 stays there. I add 1 to the exponent, divide by 4. The 3 stays there. I now have x cubed, divide by 3. 4x squared divided by 2. 4x plus, now we want another constant. And if you don't want to use c again, because we've already used c, then use d. Or use c1 and c2. Or use c again and just make sure you know it's a different c than that c. So the last, are we okay? Okay. So the last thing, I know I'm running out of time. So if you need to go, I've already said that's fine. The last thing I'm going to do is I'm going to, I'm going to reduce. So that's gone, and that turns into a 2. Let's find D, or whatever you're calling it. I'm going to go plug in what they gave me. So the Y value is 1. Minus 2 times 1 squared plus 4 times 1 plus D. Let's see, 1 plus 1 is 2, minus 2. So I have 1 plus, whoops, gosh, I'm a mess. 1 equals 4 plus D, or D equals negative 3. I mean, at this point, we're just doing some arithmetic. So that's not my answer. My final answer is f of x equals x to the 4th plus x cubed minus 2x squared plus 4x, and then minus 3. Woo! Looking good. All right, if you have questions for me, feel free to stay on as long as you need to. Thank you so much for being here today. I'm going to leave this up for the folks that are still trying to jot the last few things down. I look forward to seeing you all tomorrow. Bye-bye. Thanks, Sydney. Bye, Ryan. Thanks for being here. Maya, are we still there?